Hello, this is going to be a short video going over the Gaussian integral. If you don't already know what the Gaussian integral is, it is the integral from negative infinity to positive infinity, so over all real numbers, of e to the negative x squared dx. Interestingly, got that right that time, is equal to the square root of pi. Although, of course, we're going to be looking at this in terms of tau. On the Pi Manifesto, trying to rebuttal to the Tau Manifesto, it claims that this is an argument to say that pi is the more natural number. Because if you just look at this, yeah, pi seems to fit into the equation better. But similar to the area of the circle, it can be shown that it is tau that is behind it all along, and a 1/2 just happens to get thrown in at the end. Now, the reason I'm making a video specifically for the Gaussian integral is, first of all, because it's just very important in general, but this video is also going to be referenced to multiple times, namely in the area of hyperspheres, and then also in the gamma function. It's very important. Maybe some others, I'm not sure yet. We'll see. So just so we can get our bearings straight as far as what we're doing, here I have the best graph I could draw of y equals e to the negative x squared. This is considered to be a very important curve in mathematics, specifically probability, even though it has many applications outside of that. This is often referred to as a standard bell curve. But then what we're doing is, with the integral, finding the area of the curve throughout all real numbers, because obviously on both sides this is approaching zero. The integral does converge, and interestingly it converges to the square root of pi, although more appropriately square root of tau divided by 2. So we're just going to see how we get there and see what happens. Alright, so when first trying to solve this problem, your first reaction is going to be just trying to find that antiderivative of the function e to the minus x squared. Then you would just end up with a doubly improper integral and just take the limit of both sides of infinity. But the problem with this is that e to the minus x squared has no elementary antiderivative. Even with the most advanced integration techniques, no matter how clever you try to get, you're not going to find an elementary function that is going to describe the antiderivative of this function. So we're going to need to be even more creative than that. Alright, so I'm just going to put in the boundaries back and just set this equal to g. Now, there's nothing that you're going to be able to do right away in order to solve this, but the first step is to set to g squared. Not something you're going to normally see just basic level solving for integrals, but it's just a clever technique, and you'll see how it ends up working, because it allows us to directly solve for what g squared is, and then we'll be able to take the square root of both sides. And if you remember, there's a square root in the answer, so that makes sense. So I'm going to assume that you all know what it means to square a function. So we're just going to separate this into two separate integrals. Get my parentheses. Alright, and the reason we do that is because we're able to separate between the two in order to differentiate between the two. Just going to set these to two different variables. Could just change this to y instead of x. We're just the same, but generally it's just represented by x sub 1 and x sub 2. Okay, so here we get to see what's really going on. We can then turn this into a double integral. Alright, x1 squared plus x2 squared dx1 dx2. And now, as compared to what we have, even though now it's certainly a multivariable calculus question, this is certainly solvable as compared to what we had originally. So now we just need to go through the process of solving for this multivariable calculus problem. Alright, so here I have the same problem, and we need to figure out what we're going to do as far as solving this. So there's always going to be a lot of different things to consider when trying to solve these different integrals, although we have the advantage of already knowing what the answer is, square root of pi, or as I would like to say, square root of tau over 2. So the fact that pi or tau is involved gives us a pretty big hint that we want to convert to polar form. So we can just go ahead and do that. Alright, so I went ahead and saved us some time and wrote down what we get once we convert this all to polar form. Just want to point out because obviously any of you guys can go and look up a derivation of the Guassian integral anywhere. What I hope to do is present a case for it being tau, which is based off of. So essentially where the pi or 2 pi comes from, the only location in throughout this entire thing is this upper limit of integration of the angle. It's assumed that you guys all know how trigonometry and polar coordinates work if you're watching this, but just as a reminder, essentially what you're doing is, because unlike a typical Riemann integration where you break it up, you partition the functions into rectangles, what you're doing here is partitioning the function into circle sectors. And in order to get all of the domain as you want in this case, because it's negative infinity to infinity, you need to go all the way around the circle, which of course, I just realized I have 2 tau there, that's pi tricking me up again, is tau, of course. And so once we break it down, we are left with a fairly simple question. I'm sure you guys can figure this out, but I'll just go ahead and get that all written out so you can see exactly what happens. Alright, and so when you go ahead and do the basic math, here's just a u sub. Here's about as simple of an integral as you can get. This one's going to be equal to tau, this one is equal to 1/2. Now to summarize, after squaring the Gaussian integral, doing some clever manipulation, just realized I erased something at one point, converting it to polar coordinates, the polar part section, or rather the angle, when measuring in, radians of course, yields tau. And then the other part, which is not exactly mathematically rigorous to say represents the function, but it's a decent equivalent to say yields 1/2. Of course, when you multiply it together, you get tau divided by 2. Now, if you remember, at the beginning we squared it, so when g squared equals 2, g right up here, so you guys can see better, equal to the square root of tau divided by 2. I'm just going to erase. You guys don't need to see any of that. And now it's not letting me write. Alright, so there you go. Alright, and so as I said at the beginning of this video, the main purpose of having this as a separate video is because it's very important. It's often used as a main arguing point by the pi people, as we can call them, which makes up 99% of people that know math. But anyway, Gaussian integral is often cited, and so what I was hoping to do is just, first of all, just break down how tau is what still naturally comes out of the equation, and just like in the area formula and many other equations, a 1/2 just seems to appear out of nowhere, which, you know, take it what you want. You can interpret what that means, but anyway, also this is going to be referenced in several other arguments that I make when I'm talking about the area of the hypersphere. Instead of just going over all this, it's going to direct you here. Same with the gamma function, and like I said, there may be more. And so, first of all, I would just want to say, while I would like to be, I'm not quite clever enough to have come up with this all on my own. And so I'm just going to be providing links on where I first found this information. I'm sure you could look up the mathematicians who first worked this out. I'm going to guess it was Gauss, if that's even how you say his name. But I'll see you next time. And if you want to see how this is used, such as, of course, in the area of a hypersphere, very interesting stuff, be sure to check that out in the area of a circle video.